Here we will talk about the second approach to dynamic analysis, the impulse-momentum approach. The impulse-momentum relationship refers to the relationship that the impulse applied to the object is equal to the change in object's momentum. This relationship, which is derived from the Newton's second law, allows us to understand how hard and for how long we need to apply the force on the object to cause a change in momentum. When we are talking about a single object, change in momentum translates to increase or decrease in the object's velocity because the mass of the object will likely remain unchanged. This means that the more force you apply for a longer time, the more you can speed up or slow down an object. This slide simply shows you that the impulse-momentum relationship originates from the Newton's second law. The Newton's second law states that the net force acting on the object is equal to mass of the object and its acceleration. Since acceleration is equal to the object's change in velocity over time, you can arrange the equation and see that the impulse, or force times time, is equal to the object's mass times its velocity. This also means that the impulse is equal to the change in object's momentum, or the difference between the object's initial momentum and the final momentum. Using the impulse-momentum relationship, we can see that impulse can be applied to change the momentum of the object. Specifically, when the impulse is applied in the same direction as the object's movement, the object's momentum will increase. The example of these are shown in the figures here. At the starting block, the sprinter pushes down and back on the starting block. In return, the starting block pushes the sprinter forward and upward. The total amount of push or force applied to the person over a brief time that the sprinter pushes off the starting block is the impulse applied to the sprinter. This impulse causes the sprinter's body to gain momentum in the same direction as the force applied to him. Same can be said about vertical jumping. The average ground reaction force applied to the jumper times the time he pushed down on the ground is the impulse applied to the jumper. This impulse causes the momentum of the jumper to increase upwards. This means that the jumper will gain velocity in a vertical direction. When the impulse is applied in the opposite direction as the object's movement, the object's momentum will decrease. Examples of this can be seen during landing or catching. Landing occurs in running and jumping. When the person lands, the ground reaction force is applied to the person at his or her foot and pushes the body upward. This upward force applied over time is the impulse applied to the person. While this impulse is directed upward, the body moves downward during landing. Therefore, the impulse is applied to the object in the direction opposite of its motion. This impulse causes the person's momentum to decrease. When the person is coming down, he or she will have a downward velocity. Landing will cause that velocity to decrease to zero before the ground reaction force will start to push the runner upward again. When the person's velocity decreases, its momentum will also decrease. Rearranging the impulse-momentum relationship to look like what's on the right side is helpful in understanding how you can change the object's velocity. Looking at the equation, you see that the change in velocity of an object is proportional to the net force applied to the object and the time over which the force was applied. This means that the greater the net force applied and longer that force is applied, the more you can speed up or slow down the object. The equation also shows that the change in velocity is inversely proportional to object's mass. This means that the greater the mass of the object, smaller the change in velocity that results. In other words, to speed up or slow down an object with greater mass will require more impulse. Now, rearranging the impulse-momentum relationship to look like what's on the right side here is helpful in understanding how much force is needed to change the object's momentum and velocity. Based on the equation, you see that the amount of force you need is proportional to the object's mass and how much change in velocity you need to achieve. This means the greater the object mass and the more force is needed. It also means that the more momentum or velocity the object has to begin with, the more force you will need to decrease the momentum and velocity of the object to zero. The equation also tells us another important thing, that the force you need to change the object's velocity or momentum is inversely proportional to the time over which the force is applied. This means that the greater force is needed when you are applying the force for a short amount of time, and that force you need gets smaller when you apply the force for a longer duration. This is reflected in the idea of slowing down the car by slamming on the brake versus gradually pumping on the brake. Abruptly stopping the car in a short time requires large force, while gradually slowing the car over a long time requires less force. What we just talked about, the impulse-momentum relationship, can be applied to angular kinetics. The angular impulse-momentum relationships helps us understand how hard and for how long we need to apply the torque on the object to cause its change in angular momentum. When we are talking about a rigid object that does not change in shape, change in angular momentum translates to increase or decrease in object's angular velocity because the moment of inertia of the object will likely remain unchanged. This means that the more torque you apply for a longer time, the more you can speed up or slow down an object's rotation movement. Let's look at an example here. The example here shows how the angular impulse can increase the angular momentum and velocity of an object when the impulse is applied in the same direction as the rotation of the object. When you kick a soccer ball, the quadriceps muscle will pull on the anterior tibia to cause knee extension torque. This torque applied over time will increase the knee extension velocity, allowing the kicker to hit the ball harder. One of the reasons an experienced kicker swings the leg backwards before kicking the ball is for this reason. The more you swing back the leg, the longer the quadriceps muscle can produce torque before the foot hits the ball. The longer the torque is applied to the leg, the faster the knee will be extending when it hits the ball. Here's a different example that shows how the angular impulse can decrease the angular momentum and velocity when the impulse is applied in the opposite direction as the rotation of the object. During landing, the knee moves into flexion. The quadriceps is also active during this landing to produce knee extension torque. This knee extension torque produced by the quadriceps is in the opposite direction of the knee rotation, and therefore will cause the angular momentum and velocity of the leg to decrease. The impulse produced by the quadriceps will work to slow down the knee flexion motion in this case. Rearranging the angular impulse-momentum relationship to look like the equation on the right side is helpful in understanding how you can change the object's angular velocity. Looking at the equation, you'll see that the change in angular velocity of an object is proportional to the net torque applied to the object and the time over which the torque was applied. This means that the greater the net torque applied and longer that torque is applied, the more you can speed up or slow down the object's rotation. The equation also shows that the change in angular velocity is inversely proportional to the object's moment of inertia. This means that the greater the moment of inertia of the object, smaller the change in angular velocity that results. In other words, to speed up or slow down the rotation of an object with greater moment of inertia will require more angular impulse. Now, rearranging the angular impulse momentum relationship, like what's shown on the right side, can be helpful in understanding how much torque is needed to change object's angular momentum and velocity. Based on the equation, you see that the amount of torque you need is proportional to the object's moment of inertia and how much change in angular velocity you need to achieve. This means that the greater the object's moment of inertia, the more torque is needed. It also means that the more angular momentum or velocity the object has to begin with, the more torque you will need to decrease the angular momentum and velocity of the object to zero. The equation also tells us that the torque you need to change the object's angular velocity or momentum is inversely proportional to the time over which the torque is applied. This means that greater torque is needed when you are applying the torque for a short amount of time, and that torque you need gets smaller when you apply the torque for a longer duration. You can apply this to the analysis of landing technique. When you land while keeping your knees stiff, you are decreasing the angular momentum of the leg over a short period of time. This will result in quadriceps having to produce a greater magnitude of torque. Production of greater knee extension torque will require the muscle to produce more force, which has implications for knee injuries.